Thanks, Sai, for the introduction. So I'm Smeet. I'm currently a student at UC Berkeley, and today I'm going to talk about yield from, about why they introduced it in Python 3.3, and basic use cases, and an interesting optimization implementation that they've done. So why yield from? So the main reason they introduced yield from is because now it's easier to refactor big generators into smaller subgenerators. With your typical yield, you normally have to do a little bit of extra work if you want to call a subgenerator inside of another generator, but now it's just all handled in some Python magic. And yield from really shines when you want to handle the complicated edge cases of the send, close, and throw methods on generators. And yeah, without yield from, it would normally take a lot of messy and complicated Python code to handle these edge cases. So here's just like a simple example of yield from. On the left, this is without it. Suppose you want to iterate through the nodes of a binary search tree. You would without it, you would explicitly yield every child from a generator. But on the right-hand side, with yield from, you just simply say yield from visit B tree. What yield from does is every time you call the initial generator, it would go into yield from, yield it until the generator becomes exhausted, and then move forward. So the really cool thing that they've implemented in Python 3.3 is that if you have one generator calling a subgenerator, which calls another generator, so on and so forth, the final yielded value will go directly to the topmost generator instead of going one by one up the stack trace. And this really intrigued me, so I ran a few tests to see how much of a performance increase. But before that, simplistic benchmarks are usually bad. They don't mimic real code, and they don't really tell you that much information. But however, in this case, I think it would be fun and interesting just to do it anyhow. So just take this results with a grain of salt. So the test is I want to simulate a chain of library calls. So what I did, I nested a chain of generators 1,000 deep. I yielded around 1,000 values, and I wanted to compare 3 categories. One is callbacks, which the moment you get a value, you immediately process it, and the other 2 is yield and yield from. Just to clarify these tests, this is what it looked like. It's just a simple recursion. On the left is the yield from case. Just recurse until you hit the bottommost and then yield from a range. On the right is the callback. The moment you yield from the range, you process it using the callback. So here are the results. The callbacks blew yield and yield from out of the water. One of the reasons why is it didn't have to keep on going up and down the stack to yield values. It just got a value, processed it, and moved on with its life. But still, yield from had a significant performance increase versus yield, around 15%. I also wanted to test a more realistic use case. This time, instead of doing 1,000 deep, which is around the stack limit of Python, I did around 50 functions deep, and this is supposed to mimic a normal library call. So suppose you're using some library which has a bunch of generators on top of your normal generators. This is what it mimics. Callbacks still blew everything out of the water, and the increase of yield from versus yield is still around 15%. And then from doing these tests, the main takeaways I found was that implementing the callback approach, it was faster performance-wise, but code-wise, it was a tiny bit uglier. You first have to find these callbacks and pass them in. Suppose you want 14 different callbacks, you have all these things, and just obfuscates the code, in my opinion. While yield from has the cleanest and simplest syntax, it's just a simple for loop, and then you do whatever. So thank you for listening. Here's my information again.